The last thing I'll look at is the invertible matrix theorem. And this is one of the very important theorems in linear algebra. So I'm going to give the first part of it now, and as we continue on, we'll slowly add more and more to this theorem. We're going to let A be an n by n matrix. Then the following are equivalent. So essentially all of the statements that I write down, if one of them is true, all of them are true. If one of them is false, all of them are false. The first, A is an invertible matrix, hence the name invertible matrix theorem. The second, A needs to be row equivalent to the n by n identity matrix. The third one, A has n pivot positions. The fourth one, Ax equal to 0 has only the trivial solution. The fifth one, Ax equal to b has at least one solution for every n by 1 vector b. Part 6, there is an n by n matrix C such that C times A is equal to the identity. 7, there's an n by n matrix D such that A times D is equal to the identity. And then finally, part 8, A transpose is an invertible matrix. Before I prove this, let me discuss how to prove statements like this. In general, we need to show that number 1 implies number 2, which implies number 3, etc., all the way down to number 8. And then we need to show that 8 implies 1 to finish out the circle. However, in general, it doesn't need to be done like this. The main thing is as long as you can get from one part to any other part. So if I start at 4, I should be able to get to 1, 2, 3, 5, 6, 7, and 8. So let's try to go about proving some of these. Let's start by letting A be an n by n invertible matrix. By definition of an invertible matrix, there's a matrix C such that CA is equal to I, and a matrix D such that AD is equal to I. In particular, the definition of an invertible matrix actually tells us that C is equal to D. But this does tell us that number 1 implies number 6, as well as number 1 implies number 7. And we already know that 6 implies 1 and 7 implies 1. So this is something that I proved earlier. If CA is equal to the identity, then it's invertible, as well as if AD is equal to the identity, then it's invertible. For the next part of this proof, I'm going to suppose there's an n by n matrix C such that CA is equal to the identity. And let's suppose we do have a system of equations AX equal to 0. We can then multiply both sides by C on the left, so that's CA times X is equal to C times 0. Since C times A is equal to the identity, the left-hand side just becomes X, and C times 0 is just 0. So therefore, I started with a homogeneous system, AX equal to 0, and showed that it only had the trivial solution. So I now have that 6 implies 4. For our next piece, we're going to suppose that AX equal to 0 has only the trivial solution. Then we know that our matrix A must have a pivot in every column by work we've done previously when I talked about homogeneous systems. So this tells us that 4 implies 3. If this only has the trivial solution, then I have n pivots. And since A is square, every pivot column is also going to correspond to a pivot row. Thus, that means there's no row of zeros. So now we have that 4 implies 3, which implies 2. Next, let's suppose there's an n by n matrix D such that AD is equal to I. So now I'm assuming 7. We're going to let AX equal to B be a linear system. And we're going to temporarily let X be equal to D times the vector B. That gives us that A times DB is equal to B. Since A times D is the identity, I then get B is equal to B. So therefore, at least one solution exists. DB is a solution. It may or may not be the only solution, but it is a solution. Which tells us that 7 implies 5. 7 being that this matrix D exists such that AD is equal to the identity, and 5 saying AX equal to B has at least one solution. Next, we'll suppose that Ax equal to b does have at least one solution for every vector b. Then we know that the reduced form of A cannot have a row of zeros, because if it did, we would find some b where this solution doesn't exist. And since it has no row of zeros, we know that A is row equivalent to I. So we have that 5 implies 2. If I know at least one solution exists for every b, then we're row equivalent to I. And since we know I has n pivot positions, we have that 2 also implies 3. And we know that having n pivots does mean that there's no free variable. And that tells me that 3 is going to imply 4. If I have n pivots, then I will only have the trivial solution, since to have a non-trivial solution, I would need free variables. We also know that having n pivots will also mean no row of zeros, since this is a square matrix. And that gives us that 3 implies 5. If we have n pivots, we don't have a row of zeros, which means Ax equal to b will always have at least one solution. Next, let's suppose A is row equivalent to I. Then we know that these elementary row operations exist, where EP times e to the p minus 1 all the way down to E2, E1 times A is equal to the identity. We're going to let C be equal to the product of these elementary matrices, so now I know that C times A is equal to the identity. And that gives me that 2 is going to imply 6. And now I've shown enough equivalences to show that 1 through 7 are connected. And I highly encourage you to write out exactly what all of the equivalences are, try to start at any one of the numbers, 1 through 7, and make sure you can get to every single other number. The only thing left to show is that part 8 is equivalent, that A transpose is also invertible. This was in one of the properties that I gave before that I encouraged you to try to prove yourself, and so I'm going to encourage you to try to prove that all of these can also get you to 8, and 8 can get you to one of these.